right? So this is, this is what would happen if you allow for growth in total factor productivity. The consequences of uh, growth in total factor productivity is something that we are going to look into now. Okay, so right, so basically, what's the need for incorporating technological progress? So, like so far, we have assumed that the level of technology is constant over time, right? So that has been an assumption of ours so far. Now, as a result of this, we found that all variables expressed in per capita terms were constant in the long run. So this particular feature, if you look into several countries, if you look into several data for several countries, you would find that this is this assumption is kind of unrealistic. For example, if you look into the United States, you would find that average per capita growth rate has been positive for over 2 centuries, right? So the thing is, in the absence of technological progress, diminishing returns would have made it completely impossible to maintain per capita growth for so long. In other words, there would not have been any growth in the long run, right? So uh, the long run growth rate would have been zero if because of diminishing returns to capital. However, you know, just because there has been technological progress, steady progress in technology, we have experienced growth in per capita GDP for the United States, and this growth rate has been positive when we look into the very long run. So, for example, over 2 centuries, so over 200 years of data, if you look into that, you would find a clear positive trend in the growth rate. So, growth in the long run, in order that growth is positive, you need to have technological progress. Otherwise, the fact that there is diminishing returns to an input, this is one of the major assumptions. The entire solo growth model or any sort of neoclassical growth model hinges around this particular idea that there is diminishing returns to an input, in this case capital, right? So diminishing returns to capital would have made it impossible for growth, positive growth in the long run, had there been no technological progress. However, technological progress in case of United States clearly uh, paved the way for long run average per capita growth rate to be positive for a period of more than 2 centuries. In the absence of technological progress, as I mentioned, diminishing returns would have made it impossible to maintain per capita growth rate for so long just by accumulating more and more capital per worker. So the neoclassical economists, the early neoclassical economists of the 1950s and 1960s, recognized this problem with the classical model, so to say, and they made amends for this very basic model to allow technological progress, that is to allow the technology to improve over time. Now, these improvements sort of provided an escape from diminishing returns and therefore enabled the economy to grow in per capita terms in the long run, right? So what we would now study is how the model works when we allow for such technological advances. Okay. Now see, the first issue is how to introduce exogenous technological progress into the model. So this progress that is a technological progress, can take various forms. So inventions may allow producers to generate the same amount of output with either relatively less capital input or relatively less labor input. Uh, you know, such cases are referred to as capital saving or labor saving technological progress. Capital saving if inventions allow producers to generate the same amount of output with relatively less capital. And similarly, labor saving technological progress if the same happens with labor. That is, if inventions allow allow producers to generate same output for relatively less labor, right? So that would be labor saving technological progress. Now, inventions that do not save relatively more of either input are called neutral technology or unbiased technology, right? So what is neutral technology? Neutral invention. Neutral invention is something, it's a kind of invention that does not save relatively more of either of the inputs, right? So we'll be looking into the different kinds of neutral technologies here. So basically, the definition of neutral technological progress depends on the precise meaning of capital saving and labor saving. So there are three popular definitions, one by Hicks, the other two are by Harrod and Solo. So Hicks came up with this idea in very early, those were very early days into the development of the growth theory. Hicks, this was in 1932, during the time of the Great Depression. He came up with this idea of a Hicks neutral technology. And what exactly is a Hicks neutral technology? Hicks, according to Hicks, any technological innovation is neutral if the ratio of marginal products remain unchanged for a given capital to labor ratio, right? So you take any fixed capital to labor ratio and you find that the ratio of the marginal products, that is the marginal products to capital and labor, take a ratio of those marginal products, and this ratio should remain unchanged for any given capital to labor ratio, right? So for any given K by L, the ratio, that is MPK by MPL, should be also constant. And if that is the case, then for a kind of production function, then we can say that it's definitely it possesses the feature of a Hicks neutral technology. Such production function definitely emits the characteristic of a Hicks neutral technology. So this property corresponds to basically an idea that is frequently used in microeconomics, which we are not looking into in our current lectures. This is something called isoquants. So isoquants, basically what happens here is that the isoquants, you have to renumber the isoquants. So the number of isoquants remains same, but the ranking would differ. But that's something, that's a concept that we have not talked about because here we are solely looking into macroeconomics, and that too we are focusing on growth. So the idea is that, the intuition is that in order that the technology remains neutral, Hicks neutral, for a given capital to labor ratio, the ratio of marginal product to capital and marginal product to labor should remain unchanged. So for a Hicks neutral production function, this is the kind of technology. So Y is equal to T, as which evolves over time, Tt, that is, times f of KL. See here, we are dealing with a production function. FKL is the production function, but technology is also embedded within the production function. This is something that we did not notice before. Earlier, what happened was that, so far, the framework that we have studied so far, we have looked into something similar, but the technology term was a constant. So we were looking into A which is a constant, times the production function, which is f of KL, right? So here what you find is the technological term is a variable. It evolves over time. As you would find here, it is actually growing over time, right? So the effect of that we are going to look into. Okay, so now Harrod, the next kind of neutral technology, the idea was put forward by the economist Harrod in 1942. That was 10 years later. Um, 10 years after Hicks came up with his idea of the neutral technology. So Harrod, basically what he did was he defined an innovation as neutral if the input shares relative input shares, that is K times Fk by L times Fl, remain unchanged for any given capital to output ratio. Now notice the difference. Earlier, for Hicks, what happened was technology, you can say that technology is neutral if for a given capital to labor ratio, the marginal products remain unchanged. You're taking into account the ratio of the marginal products, and you are figuring out whether these ratios are constant or not. Okay. Here, what you're doing, you are taking into account a given level of capital to labor, and you are looking into the relative input shares instead of the ratio of marginal products, right? So relative input shares as in K times Fk divided by L times Fl. So once you find that this ratio, which captures relative input shares, this ratio is unchanged, then you can say that such a technology is Harrod neutral, right? So this is the idea that an innovation is Harrod neutral if the relative input shares remain unchanged for a given capital output ratio. Now, this was, economists Robinson and Uzawa later on showed that actually Robinson showed this bit before Harrod came up with the idea. Later on, it was developed by Uzawa. They showed that they actually came up with a specific functional form for the technology, right? So what they did was they showed that this particular definition of a Harrod neutral technology, what it did was it implied, the definition itself implied that the production function will take the following form. This form, which is represented by equation 35. So this is the functional form. Now, pay attention to the functional form. What you would notice is TT, which represents technology. This is an index of technology, and capital T is positive. So this form is called the labor augmenting technological progress, because what happens is basically if there's an improvement in technology, meaning that if there's a growth in the technology index TT, then that technological progress itself is going to raise output in the same way as an increase in the stock of labor would increase output, right? So notice that the technology factor, which is TT, appears in the production function as a multiple of L. So the technology factor or the technology index remains sort of embedded within labor. So it's kind of, we are talking about effective labor, right? So finally, economist Robert Solow came up with the definition of neutral technology as follows. So Solow, this was developed much later. He developed this idea of a neutral technology in 1969, much later than Harrod or Hicks. Um, so how he defined a neutral technology? So Solow said that an innovation is neutral. We call it Solow neutral if the relative input shares, which is um, LFL by KFK, right? LFL by KFK would remain unchanged for a given labor to output ratio, right? Or actually here, just look into, if you look into the lecture note, it's written as KFK by LFL. It would rather be the other way around. Here, for Harrod neutral, it's KFK by LFL. For Solow, it would be actually LFL by KFK if we are talking about a given labor output ratio. Otherwise, this would remain, this would be true if we are talking about a given capital to output ratio, right? KFK. So just keep in mind, if you're referring to the lecture notes, this would be LFL by KFK instead of this. Okay, everything else would remain intact. So this is the thing. So Solow neutral technology, as put forward by Robert Solow, means that an innovation is neutral if the relative input shares LFL by KFK remains unchanged for a given labor output ratio. This particular definition can be shown to imply a production function of the following form. This is the functional form, right? So see here, for Harrod, we were talking about uh, you know the technology factor being embedded within labor. Here it's the opposite. It's technology influencing capital, right? So what happens here is that technology, TT is TT is the index of technology, and TT dot is positive, meaning that technology is evolving over time. Technology is this factor is growing over time, right? So production functions of this form are called capital augmenting, just like Harrod neutral technology was called labor augmenting. But here Solow neutral is basically capital augmenting technological progress, um, because a technological improvement increases production in the same way as an increase in the stock of capital. Okay, so that's the idea that when we are talking about an index of technology in TT, we are, taking into account the fact that this technology, this index is growing over time, and production functions like these are called capital augmenting production functions, because a technological improvement basically increases production in the same way as an increase in the stock of capital, right? So this is, the Solow neutral technology is very much a capital augmenting technology, whereas Harrod neutral technology is a labor augmenting technology. Now, the question is, what is the necessity for technological progress to be labor augmenting or capital augmenting? Why do we need this, right? So suppose we consider only constant rates of technological progress, as we have done so far, right? So in the neoclassical growth model with a constant rate of population growth, what we would find, what we can prove, is only labor augmenting technological change turns out to be consistent with the existence of a steady state, right? That is, what kind of a steady state? there can be several kinds of steady state, but steady state we are talking about here is um, something in which constant growth rates of the various um, quantities are present in the long run. So in the long run, we would find the various, the per capita quantities actually of the different variables would be growing, and this growth rate would be constant. Okay, so this result can be proved. We might look into the proof later on, but right now let's talk about the assumption, the intuition and the economic understanding. Later on we'll look into the mathematics. So what is the basic idea? So the basic idea is that if we want to consider models that possess a steady state, we have to assume that technological progress takes the labor augmenting form, right? So another approach which would be substantially more complicated would be to deal with models that have no steady states at all, models that lack steady states. That is, in which the various growth rates do not approach constants in the long run. However, one reason to stick with the simpler framework that possesses a steady state in the long term, steady state that is a constant growth rate in the long run, is because the long-term experiences of countries such as USA and Germany and some other developed countries indicate that per capita growth rates can be positive and trendless over long periods of time. That's a fact, right? So you cannot deny that fact. Hence, this sort of empirical phenomenon suggests that a useful theory would predict that per capita growth rates approach constants in the long run, right? That is, the model would possess a steady state. Such a steady state, in that kind of a steady state, you would find that per capita there is growth in per capita variables, and this growth in the long run, the rate of growth is a constant, right? This is what we would be establishing, right? So if the production function is a Cobb-Douglas production function, then what would happen? So if we are talking about a Cobb-Douglas production function, Cobb-Douglas as in y equal to a times k to the power alpha L to the power 1 minus alpha, that kind of a production function, then just from inspection, it is clear to us that the form of technological progress, which is augmenting A, K, or L, will not matter for the results, right? So in the Cobb-Douglas case, basically, we will be safe in assuming that technological progress is labor augmenting. You can recall that the key property of the Cobb-Douglas production function is that in a competitive setting, the factor income shares are constant. That is a key property of the Cobb-Douglas production function. So if factor income shares are reasonably stable, as seems to be true for the US economy, but not for some other economies, we may be okay in regarding the production function as approximately Cobb-Douglas, and hence in assuming that technological progress is labor augmenting, right? So another approach when the production function is not Cobb-Douglas is is actually to derive the form of technological progress from a theory of technological change. So Acemoglu, is very famous Turkish economist, in relatively recently in 2002, he embarked on this approach, and what he did was he used a variant of the model of endogenous technological change that we will look into later on. And he found out that under some conditions, the form of technological progress would be asymptotically labor augmenting, right? So more proof, more support for using labor augmenting technological progress. Now, what would happen to the solo swan model if we take into account labor augmenting technological progress? So let's see what happens to the solo swan model. Now, what we assume is that the production function includes labor augmenting technological progress as shown by equation 35. So this is the necessary production function, right? This is the relevant production function. Now we are incorporating this particular functional form for the technology, and we are going to explore what would happen to growth in the long run. Okay. Now see, the technology term, which is TT, that grows at a constant rate X. So the condition for the change in capital stock, now that would be modified as this, right? And now if you divide both terms by L, because we are interested in exploring, investigating what would happen to per capita variables. Hence, if we divide by L, then we can very well derive an expression for change in small k, that is capital per unit of labor over time, right? So how does small k change over time? This is how small k, capital per unit of labor, changes over time. So this is, this actually follows from this equation. Is you just have to divide both sides by L and simplify. So see, this is now this is how the basic solo swan equation in equation number 19 gets modified. So the only difference between this equation 37 and our basic solo swan equation in 19, where technology was assumed to be constant over time. So the basic difference is that output per person now depends on the level of technology, right? So output per person depends on the level of technology, TT, right? So if you divide both sides by K, then what you would get is K dot by K, right? So K dot by K, why should we divide by K? Because we are interested to know how capital grows over time. K dot by K is a measure of growth in capital per unit of labor. So divide both sides by K, and you can compute the growth rate, right? So you can, this is what you would get. This would be the expression for growth rate of small k, right? Notice that here, this is how capital small k evolves over time or grows over time. Now, as in the basic solo swan model, k dot by k, small k dot by small k here equals the difference between two terms, right? So the first term is the product of S and the average product of capital, right? Product of S and the average product of capital, which is FKT divided by K. This is the average product of capital, right? And the second term is N plus delta. We are familiar with this, right? Now, the only difference that happens now is that for a given K, for a given small k, the average product of capital, which is FKT by K, this average product increases over time because TT is growing over time. So now we have growth in TT at the rate X, right? So In terms of this particular figure that we had looked into before, figure 1.4 in Barrow-Martin, observe that the downward sloping curve, that is SFK by K, because of a growth, a constant growth in TT, this downward sloping curve now shifts continually to the right. And hence, the level of small k that corresponds to the intersection between the two schedules, between the downward sloping curve and the n plus delta schedule, also shifts continually to the right. So this steady state value of capital would be shifting continuously to the right. Okay, so we can now compute the growth rate of k in the steady state. Once we have our basic concepts clear, we can now go ahead with the derivation of growth of per unit capital. Okay, so how does capital grow in the steady state, and whether this growth rate is constant? So what we have to show is that using a labor augmenting technological progress, our growth in per unit capital would be constant in the long run. Okay. Now, output per capita. So in order to do that, let us just get a few definitions clear. Okay. So this is the thing. So because of constantly growing technology, the SFK by K schedule would be shifting continuously to the right, and as a result of this, the steady state level of capital, which is K star, is also continuously shifting to the right. Okay, so now by definition, the steady state growth rate of capital, which is K dot by K star, this is constant, right? Now, since S, N, and delta, these are all parameters and these are constants. In this particular equation, what would happen is it would be implied that the average product of capital, F KT by K, this would be also constant in the steady state, right? Because of constant returns to scale, the expression for average product, basically FKT by K, this would equal F1 T by K. And this would be constant as well, only if K and T grow at the same rate. So I repeat this. Because of constant returns to scale, you can write the average product as this, right? Now this average product in the steady state, since K dot by K is constant and everything else is in terms of constants, everything else is in terms of parameters which are obviously constants, we have the average product of capital to be constant as well. Because of CRS, you can express this average product as this, right? So this is constant. How will that be possible? How do we get a constant average product of capital? That can happen only if this TT and K are growing at the same rate, right? And we know that TT is growing at the rate X, which is constant. So K also must be growing at the rate X, right? So this X should be the constant rate of growth of capital in the long run. Okay. Now, output per capita is expressed by this. This is your output per capita, right? So output capital Y is a function of capital K and T. So now divide both sides by L, and you would get small y. Capital Y by L gives you small y. Capital K by L gives you small k. TT remains unchanged, right? Now, if you divide, if you divide both sides by k, this is what you would get. Then you can cross multiply and express y as this: k times f of 1 tt by k, right? Now, tt by k, why are we interested to express the production function like this? Because this ratio is a constant, right? So k grows at the rate x, thus output per worker y should also grow at the rate x, right? So this is the idea. This is y you can express as k times something which is a constant, because this one obviously is a constant, and tt by k is a constant because both these entities are growing at the same rate x, right? So this whole functional form, this is a constant. K, however, is growing at the rate x. Hence, our per capita output would be growing at the rate x. Now, in the solo swan model, one important assumption is that the consumption per worker is a fixed proportion. It's a fixed fraction of our output per worker, right? So if S is the saving rate, then 1 minus S times small y, the per capita output, that would be the per capita consumption, right? So C is equal to 1 minus S times y, and hence the steady state growth of consumption, that is steady state growth of C, is also equal to x, because y is growing at the rate x. So constant, this is a constant. So C, which is dependent on y, should also be growing at the rate x, in which rate x is the rate at which y is growing, right? So C solely depends on y. There's a one-to-one relation between consumption per worker and output per worker. Output per worker is growing at the rate x, hence consumption per worker is also growing at the rate x. Now see, in order to sort of analyze the traditional dynamics of the model with technological progress, it will be somewhat convenient to write the system of equations in terms of variables that remain constant in the steady state, right? So variables that remain constant in the steady state. This is very important to note. What variables remain constant in the steady state? So since K, small k, capital per worker, and TT, that is a technological index, grow in the steady state at the same rate, we can work with the ratio of small k and t, right? This is the ratio of small k and t. And that is basically capital per unit of effective labor, right? Because what is small k? Small k is capital per unit of labor, right? So k hat, which is defined by small k divided by t, essentially that is equal to capital K divided by L times T, which is total capital per unit of LT. And what is LT? LT is effective labor, right? So labor times technology is, how productive. It's a measure of how productive this labor is, how productive a certain unit of labor is. So if we are employing L, then, the effectively L times T is the how this labor is contributing towards output. Okay, so capital per unit of effective labor becomes capital K divided by L times TT instead of just K by capital K by L. Capital K by capital L would have been capital per unit of labor, right? So now capital, in this new setup, in this new setup with a labor augmenting technological progress, capital per unit of effective labor is something that remains constant in the long run, something that remains constant in the steady state. Earlier, we found that capital per unit of labor remained constant in the steady state because TT was a constant, right? So now all variables, what we will do is we will express these variables in terms of per unit of effective labor. Okay, so capital, just like capital per unit of effective labor is denoted by K hat. This is just a convention. Output per unit of effective labor is denoted by Y hat, and it's it's this very very intuitive. It follows this definition of output per unit of effective labor follows the same principle as capital per unit of effective labor. So Y hat is equal to capital Y divided by L times TT, right? So now what you can do is you can divide both sides by L. If you divide both sides by L, then this is what you would get, right? So output is capital Y is a function of capital K and L. So divide both sides by L, you would get, I'm sorry, not L, this is actually L times TT. So now we are talking about effective labor instead of labor. So if you divide both sides by effective labor, L times TT, Y divided by L times TT would give you this. So the production function would be, output would be a function of capital per unit of effective labor only, right? So output per unit of effective labor is now a function of capital per unit of effective labor. Okay, so this is the thing. So since capital and technology are growing in the steady state at the same rate, we can work with the ratio capital per unit of effective labor. So the variable if L times T is often referred to as effective amount of labor, which is the physical quantity of labor multiplied by its efficiency, that is TT. So this particular terminology of effective labor is appropriate because the economy operates as if its labor input were L hat, right? So because of labor augmenting technology, the labor input is effectively equal to L hat instead of capital L, because that's how the economy will operate. So any contribution of labor towards output would be that of effective labor, because now labor is boosted by technology. So the variable small k hat is then the quantity of capital per unit of effective labor. Okay, so the quantity of output per unit of effective labor, which is small y hat, that should be equal to capital Y divided by LTT. This is the same thing. This is the same definition, follows from the same principle of capital per unit of labor, and output per unit of effective labor is it's intensively a function of, like, it's output per unit of effective labor is it's like exclusively a function of capital per unit of effective labor, right? So this is a very neat sort of result. Now there's a one-to-one correspondence between output per unit of effective labor and capital per unit of effective labor, right? So hence we can again write the production function in intensive form if we replace y and small k by small y hat and small k hat respectively. So if we proceed as we did before, um, you know, when we derived the basic solo swan model, um, we can, what we can do is we can now use the condition that AT, earlier the AT was our technology. So AT, suppose AT is growing at the rate X. So we can now derive the dynamic equation for K hat as follows. So just following the exact same principle as with the solo swan model with constant technology. The only difference is that AT, there's an AT term sitting here, and AT is something that evolves over time. It grows at the rate X, right? So this now would be our basic solo swan equation. Now see, in the difference between the two terms is SF, everything is in terms of effective labor. Capital is in terms of capital per unit of effective labor, right? So SFK by K is now SFK hat by K hat, right? So now we are exploring the rate of growth of K hat over time. That is the rate of growth of capital per unit of effective labor. And the second term now has a growth rate X sitting here, right? So see, the term X plus N plus delta is now the effective depreciation rate of K hat, right? So N plus delta earlier was the effective depreciation rate of K, small k. Now, since we are interested in K hat instead of K, the effective depreciation of K hat is something different. It is, the rate of growth of technology plus the rate of growth of population plus the rate of depreciation of capital, aggregate capital. So, the only difference between this particular equation 39, and our basic solo swan equation, which is equation 19, aside from the hats, is that the last term on the right hand side actually includes the parameter X. So, as I mentioned, X plus N plus delta is now the effective depreciation rate for small k hat, which is capital K by capital L hat. So if the saving rate S were 0, then small k hat would decline partly due to depreciation of aggregate capital, that is capital K, at the rate delta, and partly due to growth of capital L hat, that is effective labor, at the rate X plus N, right? So following an argument similar to something that we have used before when we derived the basic solo swan equation, we can show that the steady state growth rate of k hat is 0, and the steady state value of k hat star satisfies the condition that SFK hat star should be equal to X plus N plus delta times K hat star. Okay. Now the thing is, the transitional dynamics of K hat are qualitatively similar to those of small k, right? So the transitional dynamics of small k hat qualitatively similar to those of small k as in the previous setup. In particular, we can construct a picture like this, in which the horizontal axis involves k hat, and downward sloping curve is now SFK hat by k hat, and the horizontal line is at the level X plus N plus delta rather than N plus delta, right? So this would be X plus N plus delta. So the new construction can be actually shown in a figure. I'll show you that figure in the next class, and we are going to analyze that figure, and we can use this as we had used this particular figure representing the basic Solos-Swan equation in order to assess the relationship between the initial capital value, which would now be k hat naught, and the growth rate, which now would be k hat dot by k hat. So now the initial value would be the initial value of capital per unit of effective labor, and the growth rate would be the growth rate of capital per unit of effective labor. So small k hat dot by small k hat. So in the steady state, the variables with hats, that is k hat, y hat, c hat, are now constant, right? So therefore, the per capita variables small k, small y, small c now grow in the steady state at the exogenous rate of technological progress, which is x, right? So we always have the condition that is 1 by k hat times dk hat by dt, that is equal to k dot by k minus x, right? Hence, if you are to do the math, then 1 by k hat times dk hat dt, that would equal to 0, and hence k dot by k would be equal to x. Similarly, y dot by y, c dot by c, these would also be equal to x. So the idea is that the level variables, which is capital K, capital Y, capital C, actually grow. So the level variables, capital K, capital Y, capital C, actually grow accordingly in the steady state at the rate n plus x. That is the sum of the population growth and the technological change. Notice that as in the prior analysis, that neglected technological progress shifts to the saving rate or the level of production function affect long run levels, that is k star hat, y star hat, and c star hat, but they do not affect the steady state growth rates, right? So as before, these kinds of disturbances basically influence growth rates during the transition from an initial position. This initial position, we are going to look into this. Initial position would be represented by k hat naught, and we'll be studying the transition from this particular initial position to the steady state value, which is k star hat, right? So k star hat would be the steady state value, and we are going to study the transition from the initial position represented by k hat naught to the steady state value, which is k hat star, right? So more on this in the next lecture. Okay, so any questions? If you have any questions, you can ask me. All right then, so we'll pick up from here tomorrow.